Now, our last talk of the morning session, we have Stéphane de Ascoli.
Hi everyone, I'm Stéphane Ascoli. I'm going to present recent work in collaboration with Maria Refinetti, Levent Segun, Giulio Biroli, and Florent Zacala from both ENS Paris and Facebook AI Research. And I'm going to discuss, it's basically going to be a two-part talk trying to reconcile the double descent curve with previous knowledge, which it's seemingly in conflict with. So the first part of this talk is going to be about reconciling double descent with the classical bias variance trade-off, which you're probably all familiar with, but I'm just going to reintroduce quickly. So in machine learning, you expect that as you increase the number of parameters in the learning model, you should encounter two phases, the underfitting phase, where the variance is low, but the bias is high, the overfitting phase, and then somewhere in between, you should get a soft spot where the test loss is good. So you expect the test error to follow a U-shaped curve. However, as has probably been mentioned a couple of times by now, this is not the true story in deep learning often. What you instead see is that as you increase the number of parameters in a deep neural network, you're typically going to observe the U-shaped curve in an underparameterized regime, but then you're going to observe an interpolation threshold when the number of parameters is of same order as the number of training examples, where the test error generally peaks in absence of regularization. And then beyond this interpolation threshold, you're going to observe a monotonous decay of the test loss, so improvement of generalization in the overparameterized regime. Note that the interpolation threshold coincides with the point. So this is exactly the point where the training error vanishes. Now, notice that you can suppress this overfitting peak at the interpolation threshold by performing regularization, for instance, here by early stopping. Also, you can average the predictions of differently initialized neural networks, which we call ensembling, and this also gives some regularization, suppressing the overfitting peak. So we like to try and understand these two phenomena and also try and reconcile this, this double descent curve with the classic bias variance trade-off and try to understand what is happening to the bias and variances. So the model we're going to study is going to be the random feature model, which was first introduced, I think in 2007 as an approximation for kernel methods on large data sets. But recently it's attracting quite a lot of attention in theory because it's been shown to be a good model for the double descent curve. Because in contrast with simpler linear models where the input dimension is necessarily tied to the number of parameters, here you can separate these two quantities. Also, what's interesting for us is that you can see a random feature model as a two-layer network with a fixed first layer. And the fixed first layer is nice because it enables us to mimic the effect of initialization in neural networks. Also, it's been shown that overparameterized neural networks do behave like random feature models in a particular initialization scheme. And therefore, our results are potentially relevant for the lazy regime of neural networks. So let me introduce notation. So our data set is denoted as X. We have N training examples. Input dimension is D. And the number of parameters, so here the number of nodes in the hidden layer is denoted as P, so it's the number of random features. Now we have the pointwise nonlinearity sigma. We're going to take it to ReLU in this first part of the talk. And all the quantities, so the data set X, the random features theta, and the weights of the teacher, the linear ground truth beta are going to be sampled from standard Gaussians. So our student is going to take the following functional form, and the teacher function, so the ground truth is going to be simply a linear function of the inputs with some added noise. So to train our model, we're going to simply use mean square loss with some added regularization lambda, and we're going to evaluate the test loss by considering the mean square difference on a fresh sample, again, a Gaussian sample. So as I said, our objective is to try and understand what is happening to the bias and variance. So in this case, we actually have several sources of variances, right? Because we have several sources of randomness in our problem. The first source of randomness we're going to decompose is the randomness due to the random labels affecting the teacher, which we denote as the noise variance. So as you can see pictorially here, what we're doing is essentially averaging over the noise here to get an average predictor, which is closer to the ground truth in blue. And the size of this circle is essentially the variance due to the noise and labels. Now, sequentially, we can then remove the variance due to the sampling of the random features. And as you can see, we get an average predictor, which is again closer to the ground truth. And this is the corresponding variance. Now, the last step is to remove the residual variance due to the sampling of the data set. And the final averaged predictor. So we really have our three sources of variance. And sorry, I think I'm having an issue. Can you still hear me?
We can hear you.
Great. Okay, I was just wondering. Okay, good. So we have these three sources of variance and we have our residual bias. Okay, and so to study these various terms, we're going to go to the classic high dimensional limit where the number of training examples, input dimension, and number of random features all go into infinity with their ratios fixed. So the test error follows the usual double descent curve. And what we're interested in is these variance terms. So as you can see, the noise variance diverges just like the test error at the interpolation threshold. And the initialization variance, which is the one due to the sampling of the random features, also diverges. And this is why we called our paper the double trouble, because these are really the two terms lying at the heart of the double descent curve, because they're also the ones which decay with overparameterization. Essentially, as we overparameterize, we're averaging over more features. We're kind of removing the noise in this fashion. What about the two residual terms? Well, as you can see, the sampling variance and the bias have a slightly different behavior. Instead of diverging, they remain finite at the interpolation threshold. In fact, you can see a phase transition. And beyond the interpolation threshold, so in the overparameterized regime, they just stay constant. Okay, so they're harmless. What's also nice with the study of the initialization variance is that it enables us to see what happens if we remove this initialization variance by averaging the predictions of different networks. So they differ by the sampling of the random features, but they're trained on the same data set. And as you can see, as you increase the number of learners you average the predictions of, you see that, of course, the test error reduces, but more importantly, you can see that the peak at the interpolation threshold is the most affected. Okay, and if you go to the limit of infinite k, so if you average the predictions of an infinite amount of learners, what's interesting is that you're just left with the bias, and therefore the test error displays this characteristic plateau after the interpolation threshold. Notice also that the asymptotic error you get by increasing p to infinity is the same one as you get increasing k to infinity. So whether you increase the number of features by ensembling or overparameterizing, in both cases, you approach the same kernel limit. Okay, so in this first part of the talk, we basically reconciled the double descent curve with the bias variance trade-off by showing that the bias variance trade-off still holds in the classical regime before the interpolation threshold. And what happens beyond this interpolation threshold in the modern regime is a monotonous decay of the test error, which is due to the variance actually reducing and the bias remaining constant. Okay, so the second part of this talk is going to be about reconciling the modern double descent we observe in deep learning with a much more ancient form of double descent, which was discovered in the 90s. So first of all, let me introduce two kinds of double descent. The first one can be seen as we increase the number of training examples in a learning model. And of course, you're going to see a peak when the number of parameters is of same order as the number of examples in the dataset. And this is what we call the parameter-wise double descent. But in deep learning, you can also observe sample-wise double descent if you instead increase the number of training examples. You could expect that as you have more data, generalization always improves. But instead, there is a peak when n is of same order as p. So these two curves are basically almost the same. They kind of look the same. However, there is one thing that's a bit weird, is the fact that the peak we observe in deep learning occurs when n is of same order as the number of training parameters p. So if we plot this overfitting line in the NP phase space, it's just along a diagonal line. But what happens if you consider a linear network? In a linear network, you have lower expressivity, and therefore the interpolation threshold occurs lower in terms of training examples. And the corresponding peak, which we call the linear peak, occurs not when n is equal to p, but when n is equal to the number of input dimensions d. And so the overfitting line is vertical in the NP phase space. So now you could wonder, what happens? Is there something in between these two scenarios? What if I had an activation function which is pretty much linear, but for instance, if you think of a tan H with a high saturation value, am I going to see a peak somewhere in between these two peaks? Well, what we show in this paper is that in fact, both these peaks can coincide. And this is basically telling us that the linear peak and the nonlinear peak, which are often conflated in literature, are actually two very different phenomena because they can both coexist. So what we'd now like to understand is what are these peaks caused by? So they appear to be different phenomena. So do they have the same sources? And do they behave differently in practice? So to investigate this, well, we're going to use the same notations. So the same data set with a label generator with some added noise. And we're going to perform, again, regression tasks. And the first model we're going to consider is, again, the random feature model with a linear ground truth. And what's the extra notation, which is important here, is Z, the projected data set, on which we're effectively performing linear regression. And in particular, the covariance of this projected data set, sigma, which we call the random feature gram matrix, is going to be of prime importance to studying the overfitting peaks. Now, the more realistic model we confront these results to is a teacher-student task involving 3-layer neural networks, where both the teacher and the student have the same functional form. And the student weights are trained by gradient descent. And we mimic regularization by adding some weight decay parameter gamma. Okay, and so let's look at the NP phase space I mentioned previously. So here I'm plotting the test loss of the regression task in the NP phase space. Note that on the left-hand side, on the random feature model, P is the size of the hidden layer, whereas in the deep network case is the total number of peak, which is the nonlinear peak, and then another line at n equals to d, which corresponds to the linear peak. And you can really see this very clearly in both cases, which motivates us to study these two overfitting peaks by looking at the random feature model directly. So again, we go to our usual high dimensional limits, where we have a lot of results in the random matrix theory literature. In particular, we know that the behavior of the nonlinearity can be summarized by these two parameters, eta and zeta, whose ratio is effectively a degree of linearity of the activation function. For example, we can vary this degree of linearity from 0 to 1 by taking piecewise linear functions and going from this absolute value in blue to the linear function in yellow. And what we see is that this amounts to increasing the size of the linear peak and decreasing the size of the nonlinear peak. So the degree of linearity of the activation function is really governing the relative importance of these two peaks. And we'd like to provide a theory for this. To do this, we examine the eigenspectrum of the random feature gram matrix, which has been studied in recent papers. In particular, the spectral density was obtained by this paper here. And essentially what this paper shows is that in the high dimensional limit, the nonlinear projection amounts to a linear term plus some added noise. And so we can start by analyzing these two terms separately. The first term is going to yield a spectral density, which is called a product Wishart matrix, which looks a bit like a Marchenko-Pastur distribution. In particular, you see that the spectral density has vanishingly small eigenvalues when n is equal to d. Now, if we only consider the nonlinear parts, we're instead going to observe a Marchenko-Pastur distribution where we're going to observe vanishingly small eigenvalues when n is equal to p, and this is what causes the nonlinear peak. Now, what happens in the intermediate case where the degree of linearity is between 0 and 1? Well, typically, for instance, for tan H, we're going to observe something like this. What you can immediately see is that this spectrum is, in some sense, superposition of the two spectra. For instance, you can still see the vanishingly small eigenvalues at n equals to p. However, there is one non-trivial interaction between these two spectra, which occurs when n is equal to d. And essentially, it amounts to an implicit regularization of the vanishingly small eigenvalues you could observe in the linear case. So really, the action of the nonlinearity is to implicitly regularize the vanishingly small eigenvalues causing the linear peak. Now we're going to investigate the phenomenological consequences of this implicit regularization. First of all, we're going to study what these two peaks are actually caused by. So as we stated previously, the nonlinear peak is caused by an interaction between the noise variance and the initialization variance. In contrast, you can see that the linear peak, which by the way, you can only see at very high noise when the signal to noise ratio is rather small, you can see the linear peak is only caused by the noise variance. And the consequence of this is that if there's no noise in the labels, the nonlinear peak survives, but the linear peak completely vanishes. And this explains the puzzling observation in deep learning that you can overfit even if there's no noise in the labels, because the initialization of the random features really plays the role of a noise. Also, two other phenomenological differences you can observe between these two peaks is how they're affected by regularization and how they evolve during time. First of all, if you regularize, you can see that the nonlinear peak, so for instance here, I'm regularizing in the deep learning model by adding weight decay, you can see that the linear peak is strongly mitigated by the regularization, whereas I said that, yeah, the nonlinear peak is very affected, but the linear peak is hardly affected at all. And this makes sense because it's already implicitly regularized. So further explicit regularization doesn't affect the peak much. In the same vein, you can see that if you look at the time dynamics of training, so I plot the phase space at different times, you can see that the nonlinear peak appears much later during training. And this can be understood in the same way because stopping early is equivalent to regularization, and therefore it makes sense that we can't see the nonlinear peak in this plot here. So to conclude, I'd like to compare this triple descent we just presented with two other forms of triple descent, which were recently exposed. The first one here on the left was shown in the linear regression model, where the input data has a particular block covariance, and basically the two blocks of the covariance matrix cause these two peaks. But since we're just dealing with a linear model, both these peaks are what we would call linear peaks. And so this is a very different form of triple descent that we just showed. Also, another paper studied a triple descent as a function of the number of training parameters, which we called P in our case. And in this case, they see two peaks. And again, this is due to the particular structure, not of the input data, but of the random feature gram matrix, as we called it, which has two blocks because they're essentially considering the random features of a two-layer, the NTK features of a two-layer network. And so both these peaks are actually what we call in our paper nonlinear peaks. And I think the abundance of papers at the moment which are studying multiple non-monotonicities in the test loss profiles highlights the importance of distinguishing peaks into really linear and nonlinear peaks. Thank you very much for your attention.
Thanks so much. Do we have any questions?
Hi, I have a question regarding, you mentioned that the first peak was still there even with regularization. Is that's not the
Yes.
case in linear models? So do you know what is the difference?
Yeah. Yeah, so the difference is actually due to the fact that in linear models, you don't have this implicit regularization due to the nonlinearity. And what I'm saying is not that the regularization has no effect at all. Actually, here you can see that regularization does have a small effect on the linear peak. But the fact is that the effect is much smaller than for the nonlinear peak because it's already implicitly regularized. So further regularization doesn't have that much effect anymore. And it's well known that regularization is particularly strong as soon as you switch it on, as soon as you take a tiny but non-vanishing regularization parameter, it's strongly going to affect the peak. And this is why it's less affected on it has less effect on the linear peak.
But in your experiments, it still disappears. So the second peak disappears faster than the first one.
Exactly, yeah. Now, there is something that I could emphasize more on is that these peaks can really only be seen if you have a lot of noise in the, so here, for instance, the signal to noise ratio is smaller than 1. And precisely because there's this implicit regularization phenomenon, the linear peak is harder to see. And I think this is why it hasn't been so much discussed in the literature. The key point of this paper is less about presenting the triple descent curve, but more about sort of really understanding what are the sources of these two peaks. In practice, you're not going to actually be affected by this triple descent curve if you're a practitioner.
Thank you. We also have a question from the audience. From Cameron Harris, we have very interesting talk. Do you think that studying the eigenvalues of these gram kernel matrices is an approach that will work in all regimes, e.g., when the target function is fully nonlinear or a combination of linear and nonlinear parts?
Yeah, so that's a good question. I mean, I would tend to say yes, although of course it would be, I mean, everything becomes more difficult in that setup. But here we can see that we confronted these two models, right? The random feature model, where the ground truth was linear, and the deep learning teacher-student task, where the ground truth was more complicated. It was a 3-layer network, and we really saw that the results are very similar in both cases. We really keep the same intuitions. So I mean, probably there's something at play which is very similar in terms of the so in the case of the deep networks, of course, you don't have this random feature matrix, but you could assume that the covariance matrix of the NTK features, studying the eigenvalues of this matrix, would be useful to understand the overfitting peaks, I believe.
Excellent, thank you. Since we're right at time, let's take other questions to gather down into the poster session, which will be starting, I guess, now. And remember to vote for your favorite poster.